Pressure is defined by the equation P equals F over A, but you might already be familiar with the other equation that relates to pressure in a fluid. Now, what we're going to do today in this lesson video is understand how to use that equation correctly and how to apply it to the classic examples of the barometer and the manometer. Let's start off with this container of water. Don't worry that the 10 centimeter line seems a bit off. It's got water in it, which has a mass, and so there will be a weight, a force, and hence a pressure acting on the bottom of the container. Let's say the density of water is 1 gram per centimeter cubed, and its depth is 10 centimeters, and its area is 10 centimeters squared, giving a volume of 100 centimeter cubed. So since the density of the water is 1 gram per centimeter cubed, that means the total mass is 100 grams, or 0.1 kilograms. Its weight is 0.1 times 10, that's 1 Newton of force. Now, using pressure equals force over area, and the area was 10 centimeters squared, remember, we get 1 over 10 equals 0.1 newtons per centimeter squared. Right, I think we'd better get that into newtons per meter squared. So if you remember how centimeter squared to meter squared means dividing by 100 times 100, because we're in 2 dimensions. So 0.1 newtons per centimeter squared becomes 0.1 over 1 over 100 times 100, which is 1,000 newtons per meter squared, or 1,000 pascals. Oh, phew, right. That was quite a bit of work to get there, but we have just worked out that the pressure of the water acting down and found that the pressure is 1,000 pascals. Now, obviously, there is going to be a quicker way. So let's look at what we actually did. We took the equation P equals F over A. So with F equals ma, that means we can write that down as equal to mg over a. G is the acceleration due to gravity. So that's going to be equal to density times volume g over a, because mass is the density times the volume. All right, stop there. Look at the equation and you can see we've got volume on the top and area on the bottom. Volume is height times area, so volume divided by area equals height. So we can change that, equals density times h times g. And that gives us P equals rho gh, where rho is the Greek symbol and it's used to represent density. Now, I think that's quite amazing, really. To find the pressure underwater, you don't need to know how much water there is, you just need the depth and the density. The area doesn't matter. That's not the whole picture, though. It's not even the whole equation. Think about this. So what do you think? What if you now push down on the water? What happens to the pressure at the bottom? Well, it seems fairly clear to me. If you push down on the water, the pressure at the bottom will increase. So, how do we calculate the pressure at the bottom? Have a think. Okay, pause if you want more time. Well, there's the pressure from our hand pushing down, and there's the pressure from the water as well. So, the pressure at the bottom, P bottom, equals the pressure from the hand plus the pressure from the water. And with the pressure from the water being given by that rho GH equation. And at the top, well, the pressure is just that the pressure at the top is pressure at the hand. Okay, so we haven't gone into the water yet, so it's just the pressure due to the hand. So the pressure due to the depth of water is referred to as the change in pressure, delta P. And the depth is the change in depth, delta H. And that gives us this equation, delta P equals rho G delta H. Now let me take the hand away again now. What is the pressure at the bottom now? Think carefully. Well, the difference in pressure between the top and bottom is given by delta P equals rho G delta H, but there is still some pressure at the top due to the air. This means that the pressure at the bottom is P equals P atmosphere plus rho G delta H. When answering a question, pay attention to the wording. If it asks for the pressure at a certain depth, you need to use P equals P0 plus rho G delta H. But if it asks for the pressure due to the liquid at a certain depth, you only need delta P equals rho G delta H. Alright, so now that's sorted, let's put it to use. Barometers are machines designed to measure the air pressure. This is useful for weather forecasting and it's just a good use of the science. Barometers have a vacuum in the top, which means there is no air pressure up here. Now, the significance of that is that the pressure at point A here is P equals P0 plus rho G delta H, but since P0 equals 0, that simplifies to P equals rho G delta H here. Nice and simple. The other surface of the liquid down here is exposed to the atmosphere, so it has a pressure P atmosphere acting on it. If I go down a little, the pressure is P. If I move over, the pressure must be the same since they're at the same level. In the middle, it's also the same level. So the pressure must be the same even though there is this tall column of liquid here. Now, to simplify things, I'm going to bring the positions up a bit to this surface. As said, the pressure at all these places must be equal. P atmosphere, rho G delta H. So, P atmosphere equals rho G delta H, where delta H is the height difference between the two liquid surfaces. The other device we need to look at is the manometer. And in this example, the gas inside the thistle funnel has been compressed by the water, making it higher pressure. As you can see, the liquid in this manometer has been pushed down on the left, going up on the right. Now the pressure on the left at the dashed line must equal the pressure on the right. The only difference from the barometer is there is no vacuum, so the maths changes slightly. On the left, pressure is P equals P gas. On the right, P equals P atmosphere plus rho G delta H. So P gas equals P atmosphere plus rho G delta H. And as long as we know the atmospheric pressure, we could use a barometer for that, and the density of the liquid, we need to know that as well, all we need to do is measure delta H, the height difference between the two liquid surfaces. So that's pressure in fluids. Barometers and manometers are important applications, but as long as you always remember to measure the height difference between the two surfaces of liquid, then you should be fine. Now, another thing to note is the use of mercury in barometers, and because mercury has a much higher density than water, it means that for a certain amount of pressure, it doesn't rise as much, and that means we can make useful barometers. If you want to, you could actually go off and calculate how tall a water barometer would need to be in order to measure atmospheric conditions.